We often assume learning to pilot an aircraft is essentially a specialized form of driving. Push a pedal to accelerate, turn a wheel to change direction. But the Federal Aviation Administration considers this analogy misleading. Unlike a car, tethered to a two-dimensional road, an aircraft operates within a three-dimensional fluid environment. Mastering this environment requires coordinated manipulation of three spatial axes: pitch, roll, and yaw. Cockpit inputs physically map to aerodynamic control surfaces. The yoke moves elevators and ailerons for pitch and roll, while floor pedals deflect the rudder to control yaw. Total mastery of these inputs is the ultimate objective of flight training, a concept known as airmanship. Airmanship is a measurable set of skills: subconscious muscular coordination, precise timing during maneuvers, and an intuitive sense of airspeed. The most critical, physical component of this skill is control touch. This is the ability to sense the aircraft's attitude and the aerodynamic forces acting on it through the varying physical resistance transmitted directly through the flight controls. In early, lightweight aircraft, this touch was a direct physical struggle, a literal battle against the wind hitting the wings and tail. As aircraft evolved in size and speed, engineers were forced to sever this direct mechanical link to protect pilots from the massive aerodynamic loads involved. This created a new engineering challenge: the need to artificially synthesize a physical control touch that is no longer naturally present. Without this engineered feedback loop, the human brain cannot process the aerodynamic reality of high-speed flight, a disconnect that can make even the most advanced aircraft difficult to control. To understand how this works, we have to look at the baseline mechanics of a standard training aircraft. When the pilot pushes the yoke, motion travels through push rods and cables to deflect the elevator. Airflow strikes the surface, generating immediate aerodynamic resistance. This force translates backward into the yoke, letting the pilot feel the unadulterated weight of the wind against the airframe. This one-to-one mechanical ratio is ideal for small planes, but it creates a crisis as airframes grow larger and faster. This chart shows the formula for dynamic pressure. Doubling an aircraft's airspeed quadruples the aerodynamic resistance on its control surfaces. Since dynamic pressure increases with the square of velocity, the load on the controls can quickly exceed the limits of human muscular strength. Early engineers tried to solve this with complex gearing systems, attempting to provide pilots with a mechanical advantage. They also developed servo taps, small hinged surfaces that use local airflow to help push the massive primary control surfaces into position. Eventually, these mechanical workarounds reached their limit.